In the previous video, we saw how we could represent a straight line using a vector equation. In this video, we're going to see how we can take that knowledge and combine it with some of the concepts that we've seen throughout the rest of this DVD in order to solve a problem. Now, this video is going to bring together multiple theories that we've covered during this DVD, and thus I think it's going to act as a really nice conclusion to this DVD. So the problem that we're going to be solving is the following. Let's say that we have an infinitely long straight line. So if I drew a line on our whiteboard, we have an infinitely long straight line. And let's say that we also have a point in space. That point's not on our line, it's floating somewhere out in space. And I'm going to call that point R. Now what I'm interested in doing is finding the shortest distance from R to our line. Now it turns out that the shortest distance from R to our line is the perpendicular distance from R to our line. That is to say, if we created a line from R such that it touches our infinitely long line, if it met our line at a right angle, the length of this new line is the shortest distance from our point R to our infinitely long line. So we're after the perpendicular distance, the distance if we created a line from our point to the infinitely long line such that it meets at a right angle. Now we could represent this line segment, the line segment that's the distance we're trying to find, as a vector v. So we could represent this as a vector, which we can call that vector v. And what we're interested in finding, therefore, is the length of v. So our perpendicular distance is equal to the magnitude of v, the length of that vector, because of course the length of the vector is going to tell us how far we have to travel from R to touch our line, and we know this is the shortest distance we'd have to travel to touch our line, because if we traveled to any other points on our line, we would be traveling a greater distance. This is the shortest distance, the perpendicular distance. Now if we're going to represent our line in some way, our infinitely long line, it makes sense that we're going to represent this using vectors, because I said in the introduction that that's exactly what we're going to be doing. So if we want to use the vector equation to represent this line, we know that that vector equation is that a point on the line represented by the position vector p is equal to p1 plus t multiplied by d, where p1 is a position vector representing a point on the line, t is a parameter that controls how far along the line we travel from that point, and d is the direction of that line. So we know that we're going to need a point on our line that's going to be this point p1. So it's a point on the line. We could create a point here, say. It's the point p1, and that's represented by this position vector p1. So if we had our origin, we know that we've got a vector that travels from our origin to our point p1, and this is the position vector p1. And we're also going to need this direction vector d that's representing the direction of our line. Now in this case, to solve this problem, it's actually going to simplify our calculations later if d, the direction of our line, is represented as a unit vector, if d has a length of 1. So instead of creating d, what I'm actually going to do is I'm going to use d hat. So I'm using a unit vector version of d, and we can draw that on our diagram as something like this. So we have d hat, we have d, it's our direction vector, but it's also a unit vector. It has a length of 1. Now if we're representing all of these pieces of information as vectors, it makes sense to represent our point R as a position vector. So we can represent point R by using a position vector. And we can call that position vector R. And also, we could represent the point that's known as the foot of the perpendicular. Now that point is a point on our line that is the closest point to the point R. In other words, it's the point on the line where our vector v would touch that line, and we can call that point Q, and we could represent that point as a position vector as well. So we could create another vector from our origin up to point Q, and this is going to be the position vector Q. So we're representing our entire problem using vectors, and that means we can apply some of the theories and concepts that we've seen throughout this DVD to start building relationships between these vectors in order to solve our problem. And the problem again that we're trying to solve is the perpendicular distance from R to our line, which we know is the length, the magnitude of this vector v. So we're trying to find the length of v. Well, in order to find the length of v, we're going to need to know v itself. What is v equal to? Well, we can see from our diagram that we can represent v in terms of the position vectors r and q, because v travels from r to q. In other words, we start at r and we could travel to the origin, and then from the origin we could travel to q. So just as we've used two position vectors in many videos now in order to define a vector that travels between 2 points, we can do the exact same thing here. So we can say that v is equal to, we'd have to travel down the negative direction of r and the positive direction of q. So it would be negative r plus q, or q minus r. So we can define v as being q minus r. Now we know r because r is the position vector that represents our point r, and point r is a given in the problem. When we're solving this problem, we'd know the point r, we'd know the point P1, and we know the direction of our line, because we know our line, represented by P1 and D, and we know R, we know the point from that line that we're trying to find the distance between the line and the point. The things we don't know in this case is where Q is, and therefore we don't know the position vector Q. So in our problem, we can't yet find V because we don't know the position vector Q. We do know that Q is representing the point capital Q, and that point does lie on our line. So that means that point can be found by using our equation. It can be found using the equation that some point on the line is equal to P1 plus some scalar multiple of our direction vector. So we know that Q can be found using this equation. So we could say something like this. We could say that Q is equal to P1 plus, I'm going to call this TQ multiplied by D hat. So TQ is the parameter value that we need in order to find point Q. In other words, in order to find the position vector Q. And if we can find Q and we know R, then we're able to find V. And if we can find V, we can find that perpendicular distance. So we are after one scalar value here in order to solve this entire equation. We are after the scalar value TQ. In other words, we're after the parameter value for our vector line that gives us this point, the foot of our perpendicular. So we need to find TQ. We know once we've found TQ, that's going to give us Q, which means we can find V as being V is equal to Q, which is all of this, so P1 plus TQ multiplied by D, and once we've got Q, we have to subtract R from it. So V is equal to P1 plus TQ multiplied by D subtracted R. Now we know some properties about V. We know that V here, our vector V, is perpendicular to our line. That is to say that V is perpendicular to D, since the fact that they're perpendicular is only really representing their directions. Their directions are perpendicular. We don't need to worry about the whole line, we only need to worry about the direction of the line. So we know that V is perpendicular to D. V meets D at a right angle. That means if I took V and I found the dot product of V and D of course is a unit vector, so I should just keep to the same notation the entire time. So v dot d hat is going to give us, we know the dot product is equal to the length of our first vector, the length of v, multiplied by the length of d, so the length of our unit vector d, multiplied by the cosine of, and they meet at a right angle, they're perpendicular, so the cosine of 90 degrees. But we know the cosine of 90 degrees, we've discussed this previously, and we saw it in volume 2 where we dealt with trigonometry. The cosine of 90 degrees is 0. So this is equal to the length of v multiplied by the length of d, even though we know that's 1, that's not important here, because we're multiplying it by 0, which means all of this is equal to 0. So we know that if we took v, and we found the dot product of v dot d, that is equal to 0. Why is it equal to 0? Because v meets d at a right angle, therefore they're 90 degrees to each other, therefore the dot product, which involves the cosine of 90 degrees, that's going to result in a value of 0. So if v dot d is equal to 0, and v is equal to p1 plus tq by d minus r, then we can rewrite this as basically taking this value for v and plugging it into our equation, which, because I don't know if I'm going to be able to fit it all on one whiteboard, or I might just be able to, that's equal to, or rather, we can rewrite this as, there we go, we can rewrite this as p1 plus tq multiplied by d minus r, that's our value of v. We take all of that and we dot that with d, and we know that that is equal to 0. So v, which is represented by p1 plus tq times d minus r, dotted with d, is equal to 0. So we've got this equation. We have the equation that p1 plus tq times d minus r, we evaluate all that and find the dot product of that with d, and we know that that's equal to 0. So we can expand this and maybe be able to solve for tq, because we know p1, we know r, and we know d. Again, the things that define our problem, we know the line as defined by p1 and d, and we know the point that we're finding the distance of from the line. The only unknown in this equation is tq, and we know that this equation is equal to 0, so we must be able to solve this equation. In order to do that, I'm going to expand the equation and try and solve for tq. So if we expand this equation, I need to find p1 by the dot product of d plus tq times d by the dot product of d minus r by the dot product of d. So we're going to get p1 dot d plus tq times d by the dot of d minus r dotted with d. Now the fact that we can expand this may seem a little confusing. I'm going to explain why we can expand this like this in a second when we have an easier example. In actual fact, allow me to do it now just so I don't get too carried away with myself. So if I had a plus b dotted with c, since we didn't cover this when we looked at the dot product, if I had a plus b dotted with c, I can write this as a dot c plus b dot c. Now why can I write this like this? Well, let's say that I was dealing here with a vector a that's equal to ax, ay, and az, plus a vector b that's equal to bx, by, and bz, and I'm dotting them with a vector c, which is equal to cx, cy, and cz. If we evaluated it like this, we'd see that we get ax plus bx, which would then be multiplied by cx, or actually I should probably put our vector in first. I'm trying to jump ahead one stage and that may lose people, so just in order to not do that, let's actually write this vector in. So ax plus bx, the second component would be ay plus by, and the third component az plus bz, and we're going to dot that with cx, cy, and cz. We know that's going to be equal to this multiplied by this. So we're going to get ax plus bx multiplied by cx plus this multiplied by this. So ay plus by multiplied by cy plus this multiplied by this. So az plus bz multiplied by cz. Okay, now given that we've got that, and I am running out of whiteboard, but I may be able to squeeze this in, let's look at our first term here, ax plus bx multiplied by cx. If we expanded this, we'd get ax cx plus bx cx. If we did the same for our second term, we'd then add ay cy plus by cy. If we did the same for our third term, we'd then add az cz plus bz cz. But notice, if we took ax cx plus ay cy plus az cz, that is the dot product of a dot c. If we took a and dotted it with c, we'd get ax cx plus ay cy plus az cz. Fantastic. And if we took bx cx plus by cy plus bz cz, that is the same as b dot c, bx cx plus by cy plus bz cz. Therefore, because we've got all of these added together, that is the same as a dot c plus b dot c. So that's just a very quick proof that a plus b dot c is the same as a dot c plus b dot c. I had no intention of actually going into that detail in this video, but since it does apply to something we're using in this proof, and since that's not something that I had covered up until this point, I didn't want to leave everyone just assuming that that was valid. I felt that I could quickly, on the fly, throw that proof in for you. So hopefully you followed that and can see why, as I scroll back up to explain, why a plus b then dotted with c is the same as a dot c plus b dot c. If that didn't make sense, then trust me that that is the case, and maybe look into that proof in your own time, because it wasn't something I was planning on showing here in this DVD at all, but it just happened to be appropriate to talk about it now because of the fact that it's being used in this proof. So I'm just clearing some space. I've run out of undos, which is why I'm not undoing. I'm clearing some space so that I can continue solving the problem. So please bear with me for a second. Almost there. But with anything really in vectors, because it's just dealing with the components of the vector, you can often see that the proofs are actually very easy, because all we do to prove something, if we see that something is equal to something else, if someone states that something is equal to something else, then all we really need to do is put the components into our vectors, assign the components variable names, work out what one of those things is equal to, work out what one of the other side of the equation is equal to using the components, and often you'll see that the components tell us the fact that they are true, because we'll get two equations when we expand everything that are the same, and that's exactly what we did here. Now that was getting a little bit sort of out of what I wanted to be talking about in this video, so I am now going to refresh our memory of where we'd got to in solving that problem. So if you recall, we were solving our problem, and we said that our vector v, which we'd found to be equal to p1 plus tq times d minus r, so we knew that that's our vector v, and we said v, because it's perpendicular to d, if we take the dot product of v dot d, that's equal to 0. So we took our value for v, which we knew to be p1 plus tq times d minus r, and we took all of that and dotted it with d, and as we've just seen, that allows us to expand this, now that we've seen that proof, to p1 dot d plus tq times d dot d minus r dot d. So it did take a little bit of a detour, but hopefully this video has benefited from that because you've seen an extra proof that I wasn't originally planning on showing. So we've seen that we can expand this, and we know, of course, the important part here. There we go. The important part here is this is equal to 0, and that means we can solve for TQ. Now, you'll notice, and I want to draw our attention to something here. If I was to write this as P1 dot D plus TQ times D dot D minus R dot D, you'll notice we have the dot product of these two vectors D. I want to draw our attention to this because this is actually quite significant. It's why we chose to represent D as a unit vector when we were representing our line, because D dot D is equal to the length of D multiplied by the length of D multiplied by the cosine of the angle between them. Now we know that D is a unit vector, so we're going to get 1 multiplied by 1, and the angle between D and itself, 0 degrees. So the cosine of 0 degrees, which is equal to 1 multiplied by, well, the cosine of 0 degrees is 1. So we get 1 multiplied by 1, which means that D dot D itself is just equal to a value of 1. So because D dot D is equal to a value of 1, this entire term becomes a value of 1. Which means we've now got P1 dot D plus TQ times 1 minus R dot D. Well, TQ times 1, this term right here, is equal to TQ. Anything multiplied by 1 is itself. So now our problem's actually simplified down because we've got P1 dot D plus TQ minus R dot D is equal to 0. Again, we're trying to find TQ. We know P1, we know D, and we know R. Therefore, we know everything except for TQ in this equation. That means we can simplify this equation down, and that's going to enable us to solve this equation, or rather than simplify, rearrange this equation rather, and that's going to enable us to solve this equation for TQ. So again, I just need to clear some space because I don't have much whiteboard left, and we've got a few more lines of working. So we're able to solve for TQ, because if I was to add R dot D to both sides and subtract P1 dot D from both sides, I get TQ. If I add R dot D, that disappears from our left-hand side. If I subtract P1 dot D, that disappears from our left-hand side, leaving us TQ on its own. If I add R dot D, we're going to get R dot D. If I subtract P1 dot D, we'll get minus P1 dot D, and that in itself can be written as, for the same reason as we just saw the proof for, R minus P1 dot D. So TQ is equal to R minus P1 dot D. Now that we've got that, we found that value for TQ again. We know R, we know P1, and we know D. They are the three pieces of information we need to know to solve this problem. So with those, we can now calculate TQ, and with TQ, we can calculate V. We know that V is equal to P1 plus TQ times D minus R. TQ is the only piece of information we needed to find. We've now found that, and now that we've got V, this vector that goes from R to Q, we know that we can then take the magnitude of V, that's going to be our perpendicular distance of R, from this line. So as I scroll back down, we're interested in this equation right here, because V is equal to P1 plus TQ times D minus R. We could then plug this value of TQ into that equation. Now you'll also notice, if we wanted to, with TQ, we could find the point Q, the foot of our perpendicular, because we know that Q, there it is, Q is equal to P1 plus TQ times D. Again, that TQ parameter was the parameter that defined where Q existed on our line. So now that we've got that, if we know our line equation, we can find Q. So if for whatever reason we had this point R, and what we were trying to find, rather than trying to find the distance, if you will, the perpendicular distance of the point from the line, if we were actually simply trying to find the point on the line that is the foot of the perpendicular from R to the line, we could do that using this equation and taking that value of TQ and putting it into that equation. And actually, sometimes this is more useful and more problems can be solved using that than actually finding the perpendicular distance. So sometimes it can be useful to have a point and have some line defined by a vector, and you want to find the foot of the perpendicular for whatever reason, you using it to construct some set of vectors that's going to help us solve a problem. I've actually found, when I've been working in computer graphics using vector maths, I've actually found being able to find Q to be of more use than being able to find V. But both of those are useful. Being able to find the distance or being able to find the foot of the perpendicular are both useful, and both of them rely on us finding this TQ value. So again, we know 3 pieces of information for this problem. We know R, we know P1, and we know D. So we know definition of our line using the vector equation, and we know some point that sits from that line. Given those 3 pieces of information, if we find TQ, we can find Q, which represents the foot of the perpendicular. If we find TQ, we can find V, which the length of V represents that distance. How did we find TQ? We find TQ as the dot product of R minus P1 with D. Again, we know R, we know P1, we know D. So we can find TQ in terms of what we know. We can use that to find Q in terms of what we know, and we can use it to find V in terms of what we know. Now, we've already seen the theory. I'm going to recap the theory just quickly again, because we did take that detour, and that meant there was a little bit of a break in the flow, if you will, of the theory. So I want to go through everything start to finish, just nice and simply and just in English. Now we've got everything written down. I will go through the theory once again, and then we're going to use the theory to solve an example question. And once we've solved an example question on the whiteboard here with me going through an example, I'm then going to set a question for you to work through on your own. So let's quickly go back through the theory. So we saw we had this point R, and we had a line, P1 and D. So our line's represented with a vector equation. That vector equation is any point on the line is equal to P1 plus some multiple of D. And what we were interested in finding is this vector V, the vector that travels from R to a point on the line Q such that V meets our line at a right angle. And we said in order to find V, we needed to be able to find this point Q, where Q is the closest point on our line to R. It's the point where V meets the line at a right angle. So we said we know that Q exists on our line. It is a point on our line, and that means it can be found using our vector line equation. And we can represent our point on that line, if you will, by the equation Q. So the position vector for that point on the line is equal to P1 plus some specific parameter value times D, where this specific parameter value is the parameter value we need to locate that point. So what we're interested in doing is we're interested for solving for this parameter value. Now, given that we found that parameter value, which gives us the point Q, we're then able to find V. We know that V is equal to Q minus R using the theories on position vectors that we've seen, which we can then write as V is equal to P1 plus TQ times D, which is equal to Q, minus R. Now, we also know, of course, that V is perpendicular to our line, and our line is represented in terms of direction by D. So we said that V is perpendicular to D. They're at a right angle to each other. And we said if that's the case, if we found the dot product of V dot D, that that's going to give us the length of V times the length of D times the cosine of the angle between them, that angle being 90 degrees. The cosine of 90 degrees is 0. Therefore, if we multiply anything by 0, we get 0, which told us that if we took V and dotted it with D, that would actually give us 0 as a result, because we know that V and D are perpendicular to each other. So therefore, if we took this equation, which we know is equal to V, and dotted that with D, that too would be equal to 0. And that's exactly what we did here. We took the equation that's equal to V, dotted that with D, and that is equal to 0. We then took a little bit of a detour to explain how we could expand that, and came back to show that we can expand that by taking this part and dotting it with D, then taking this term and dotting it with D, and then taking this term and dotting it with D, giving us P1 dot D plus TQ times D dot D minus R dot D. Again, that's still equal to 0. We then showed that because here we have D dot D, and D is a unit vector, D dot D is going to be the length of D times the length of D times the cosine of the angle between them. Well, the length of D is 1, so we'd get the length of D, 1, times the length of D, 1, so that's 1, times the cosine of the angle between them. They're the same vector, so there's a 0 degree angle between them. The cosine of 0 is 1, so we get 1 times 1 times 1, which means the dot product of D dot D is equal to 1. Therefore, we get TQ times 1, which simply gives us TQ. And that now gives us an equation that allows us to simplify, or rather rearrange, to find TQ. So we rearrange that equation, adding R dot D to both sides and subtracting P1 dot D from both sides, giving us TQ. And then again we used our dot product expansion, this time to factorize it back down, just to give us a nice simple form where we can find TQ. So we can find TQ by taking the position vector R, subtracting the position vector P1 from that, and dotting that with the vector that describes the direction of our line. Once we've got TQ, we know that we could use that to find V if we wanted, and then find the length of V to find that perpendicular distance. Or we could use it to find Q, and in finding Q, we'd be able to find the foot of the perpendicular, and that in itself sometimes is very useful. So that's a very brief recap over all of the theory. Hopefully, if anything wasn't clear and the logical flow wasn't clear from the first time we went through it, hopefully going back through it a little bit faster this time and without taking that detour has helped everything to sink in. So now that we've seen that theory, let's actually go ahead and solve an example question here on the whiteboard. Okay, so in order to do that, I'm going to need to bring up a new whiteboard. So I'm going to bring up a new layer really quick. Fantastic. So the question we're trying to solve is the question of the perpendicular distance between a point R, given by the coordinates 4, 2, 7, and the line defined by the point P1, which is equal to 1, 4, 2, and the direction vector D, which is equal to 0.6, 0.8, and 0. Now we know, if we know the points R and P1, we know that we can define those two position vectors. R is equal to 4, 2, 7, and P1 is equal to 1, 4, 2. So with our three vectors, R, P1, and D, we have everything we need in order to solve that problem, in order to find the perpendicular distance between R and the line defined by P1 and D. Now earlier we saw that that distance is given by the length of this vector V. So we know we need to find vector V so we can calculate the length of V, and that will give us that distance. And we've seen that that's given by this equation right here. V is equal to P1 plus TQ times D minus R, where we need to find this parameter value TQ. And we also saw that TQ is given by R minus P1 dot D. So if we were to rewrite that over on our other layer, we know that V is equal to P1 plus TQ times D minus r, and that TQ is given by r minus P1 dot D. So the first thing we need to do is calculate TQ using our vectors. Once we have a value for TQ, we can put it into this equation and calculate V, and once we have that, we can find the length of V, and that gives us the perpendicular distance. So let's start off by calculating TQ. So TQ is going to be equal to our vector R, 4, 2, 7, minus our vector P1, 1, 4, 2, dotted with our vector D, 0.6, 0.8, 0. Fantastic. So we need to first evaluate these parentheses, which means we need to evaluate that subtraction. So 4 minus 1 is 3, 2 minus 4 is minus 2, and 7 minus 2 is 5, and we're dotting that with 0.6, 0.8, and 0. And we know that the result of that dot product is going to be equal to the x components multiplied, so 3 multiplied by 0.6, added to the y components multiplied, so added to minus 2 multiplied by 0.8, added to the z components multiplied, so that's going to be 5 multiplied by 0. 3 multiplied by 0.6 is 1.8. Minus 2 multiplied by 0.8 is minus 1.6. And 5 multiplied by 0 is 0, so plus 0. So 1.8 minus 1.6 is 0.2. So the value of TQ is 0.2. Now that we have that, we can put this back into our equation for V. So we know that V is equal to, it's equal to P1, which is given by the vector 1, 4, 2. 1, 4, 2. So V was equal to P1 plus TQ multiplied by D. So that's going to be plus our parameter TQ multiplied by the vector D. Now again, the vector D was given by 0.6, 0.8, 0. So V was equal to P1 plus TQ times D minus R. So minus 427. So minus 4, 2, 7. We have everything we need in order to find V, so let's evaluate this. So it's equal to 142 plus 0.2 times 0.6 is going to give us 0.12. 0.2 times 0.8 is going to give us 0.16. 0.2 times 0 is going to give us 0. Minus 4, 2, 7. Which if we evaluate this, and actually I might not have enough room to write those values in, so I want to give myself just a little bit more room here. That should be plenty. Fantastic. So we've got 1 plus 0.12, so 1.12, minus 4 is minus 2.88. We've got 4 plus 0.16, so that's 4.16, minus 2 is 2.16, and then we've got 2 minus 7, so that is minus 5. So this is our vector V. It's equal to the vector minus 2.88, 2.16, and minus 5. So we're very close to having that perpendicular distance. What we've got, if we cast our mind back for a second, what we've got is this vector. We've got the components of this vector. What we want is the distance between R and Q. To get that, we find the magnitude of V. So we need the magnitude of V, which we know is equal to the square root of x squared plus y squared plus z squared. which if we use a calculator to solve this, that's equal to, well, minus 2.88 squared is the same as 2.88 squared. So 2.88 squared plus 2.16 squared plus 5 squared is equal to, so it's equal to the square root of 37.96. So 37.96, which is approximately equal to, if we bring the calculator back, that is approximately equal to 6.16 units. 6.16 units. So the perpendicular distance between our point R and the line defined by P1 and D is 6.16 units. So hopefully now you can see not only how we derived all of that theory earlier in this video, but how we actually apply that theory. Because although there's a lot of theory involved, there are two simple equations that we actually need in order to find the perpendicular distance. We need V is equal to P1 plus TQ times D minus R, and we need to know the value of TQ, which is given by R minus P1 dot D. Given that we know R, we know P1, and we know D, that allows us to find TQ, which allows us to find V, which obviously then, if we take the magnitude of V, it gives us that perpendicular distance. So the whole point of this exercise was to show how to apply that theory to solve a problem. Now that you've seen that, I'd like you to solve a problem yourselves on your own. So I'm going to bring up a new whiteboard in order to do that. Alright, so question 1. This is going to be the first and only question of this video because it's a little bit involved, so it will take some time to work through all of the lines of working and get an answer. So because of that, I'm only going to set the one question in this video. So this question tells us that we have a line, and that line is defined by the points P1 equal to 2, 0, 3, and P2 equal to 0, 3, 1. So we have 2 points in 3D space, and we have a line that passes through those points. We also have a third point. This point is R, and it has the coordinates minus 2, 3, and 6. This question is going to ask you to find the perpendicular distance of R from the line defined by P1 and P2. So using what we've covered both in this video and in the previous video, I'd like you to find the perpendicular distance of the point R from the line defined by P1 and P2. So go ahead and attempt to solve this on your own. Once you have a solution, or if you do get stuck, unpause the video. I'm going to work through the entire answer here on the whiteboard. Okay, welcome back everyone. So the first thing we need to do here, of course, is we need to get our problem in terms of how we already know how to solve that problem. And that means we need our problem in terms of a vector line equation. So we need to take P1 and P2 and use that to define a vector line equation. In other words, we need to find that vector d hat. Now whether we make d hat travel from P1 to P2 or from P2 to P1 won't affect the result because they're both valid definitions for our line. Sure, the direction will be travelling in the opposite direction, but in terms of the perpendicular distance, it won't have an impact. Now, personally, I'm going to just say that our line travels from P1 to P2. That's just a personal preference. That's the direction I'm going to be going in. Now, the first thing I'm going to do is calculate a vector d. Notice this is d and not d hat. So this is not the unit vector d, this is just the vector d, and I'm going to calculate that as the vector that travels from P1 to P2. So d is going to be equal to P2 minus P1, the position vectors that represent these points, and that's going to give me P2 is 0, 3, 1, minus P1 is 2, 0, 3. So that's going to give me that the vector d is equal to 0 minus 2 is minus 2, 3 minus 0 is 3, and 1 minus 3 is minus 2. Now this is d, but recall we need d hat, our equations use a unit vector because that's simplified down our workings. So I need to normalize this vector before I can use it to solve the problem. That is very important. We must have a direction represented by a unit vector for this particular theory that we're using, because of the fact that by having it as a unit vector, it simplified our workings. That means the equations that we have for finding TQ and the equation we have for finding V relies on D being a unit vector. So we know that D hat is equal to D divided by the length of D. So that means we need to find the length of D. So D, or rather the magnitude of D, we know is equal to the square root of x squared minus 2 squared plus y squared, 3 squared, plus z squared minus 2 squared. So it is equal to the square root of minus 2 squared is 4, plus 3 squared is 9, plus minus 2 squared is 4, which is equal to the square root of 17, which is approximately equal to, if I bring a calculator up, the square root of 17 is approximately equal to 4.123. Let's take this to 3 decimal places. So 4.123. Fantastic. So that's the length of D. We now need to normalize D. That means we're going to take D and divide it by 4.123, which we know from our earlier videos means we're going to take each of the components of D and divide each of the components by 4.123. So D hat, our unit vector D, is equal to, the first component of D is minus 2, so minus 2 divided by 4.123. The second component is 3, so 3 divided by 4.123. And the third component is minus 2, so minus 2 divided by 4.123. That's going to give us the vector. Again, I'll use a calculator here. So minus 2 divided by 4.123 is equal to minus 0.4851. So let's take that to 4 decimal places. So minus 0.4851. 3 divided by 4.123 is equal to 0.7276. So 0.7276. And the final component is actually the same as our first component. So that is equal to minus 0.4851. So we've now found that unit vector D, and that means we have all of the pieces of information we need to solve our problem. We have the direction of the line, we have a point that the line passes through. Now whether we choose point 1 or point 2 for that doesn't matter. I'm going to choose point 1, and we have a point that we're trying to find the distance of from the line. So you remember from our theory that we need to find the length of a vector V, which is given by, in this case I'm going to take P1, so the position vector of one of the points that our line passes through, P1 plus TQ multiplied by our unit vector D minus the position vector of the point that we're trying to find the perpendicular distance of. And we, of course, need to find that value TQ, and TQ is given by our vector R minus our vector P1 dotted with our vector D hat. So let's solve for Q. So it's going to be equal to, our vector R is the position vector of point R, so it's minus 2, 3, 6. Minus P1 is the position vector for point P1, so that's minus 2, 0, 3. And then we're going to dot that with D, and D, of course, is minus 0.4851, minus 0.4851, 0.7276, and minus 0.4851. Fantastic, which is equal to, well, minus 2 minus 2 is minus 4. 3 minus 0 is 3. And 6 minus 3 is 3. Dotted with our vector minus 0.4851, 0.7276, and minus 0.4851. Fantastic. So this is going to get a little bit messy, and I will use a calculator to solve it, but we know it's going to be equal to minus 4 times minus 0.4851. So minus 4 times minus 0.4851 plus 3 times 0.7276 plus 3 times minus 0.4851. Which is equal to, let's use a calculator. So I've got a minus and a minus. That means I know I'm going to get a positive value. So I'm simply going to put in a positive 4 and a positive 0.4851. So 4 times 0.4851. So that's going to give me 1.9404. So 1.9404 plus, I need 3 times 0.7276, so 2.1828, so plus 2.1828 plus, well, I know I've got a positive number multiplied by a negative number, so this is actually going to become a negative, and then I'm just going to multiply the two numbers together as if they were positive, just as easier on this calculator. So times 0.4851, so that's 1.4553, but we know we're subtracting 1.453. So that means our parameter value TQ is equal to 1.9404 plus 2.1828 minus 1.4553. That is equal to 2.6679. So our parameter value TQ is equal to 2.6679. Now that we've got TQ, we can hunt down, there it is, we can find V. So we've got TQ, that means we can find V. Now I have run out of space on this whiteboard, so I'm going to bring up a new whiteboard. And the first thing I want to remember is TQ is equal to 2.6679. So TQ is equal to 2.6679. I'm also going to need our value for P1. We know that that is equal to, as I hunt down, 2, 0, and 3. So 2 in x, 0 in y, and 3 is P1. We're going to need our vector r, which we know r is minus 2, 3, and 6. Minus 2, 3, 6. We're going to need our vector d hat, which I'll need some room for this. D hat is minus 0.4851 in both x and z. So minus 0.4851, and in y it's 0.7276. So 0.7276, and in z it's 0.4851, so the same as x. Fantastic. So now that we've got those, we know that V is equal to P1 plus TQ multiplied by D minus R. So we can put all of these pieces of information into that equation. So V is equal to P1, which is 203, plus TQ, which is 2.6679, multiplied by D, which is minus 0.4851, 0.7276, and minus 0.4851. And then we're taking away from that r, which is minus 2, 3, and 6. Fantastic. So let's evaluate this now. So that's equal to 203 plus, now I'm going to use a calculator to work these out, and I am going to have to simplify our values. But if I take 2.6679 and I multiply that by minus, I need to multiply that by minus 0.4851, so minus 0.4851, that gives me minus 1.294, and I could round that to 42, so minus 1.2942 minus 1.2942, which is going to be the same for z as well, so minus 1.2942, and 2.6679 multiplied by 0.7276 is 1.9412, if I round that to 4 decimal places, so 1.9412. Fantastic. So now that we've got that, we need to subtract minus 2, 3, and 6. So this just needs evaluating now. So it's going to give us, for the first component, 2 minus 1.2942 minus minus 2, so plus 2, is equal to 2.7058. So 2.7058. Our second component is equal to 0 plus 1.9412 minus 3, which is equal to minus 1.0588. So minus 1.0588. And our third component is 3 minus 1.2942 minus 6, which is equal to minus 4.2942. So it's equal to minus 4.2942. This is our vector v. So we're almost there. To find that perpendicular distance, we need the length of v, which we know is equal to the square root of x squared plus y squared plus z squared, which is equal to, I'm going to use a calculator for this, 2.7058 squared plus 1.0588 squared plus 4.2942 squared is equal to the square root of 26.8825. We take the square root of that, it's going to give us 5.18 units approximately. So the length of v is approximately 5.18 units. Now, of course, this is approximate because we've used a lot of rounding to get our results. All the way back up here, when we calculated d, back on the previous whiteboard, if you will, when we calculated d, we had to round that square root when we found the length of d. So that meant even from when we were calculating d, we were using rounding. Then in our calculations here, we were using rounding. When we found TQ, we were rounding. So there's a lot of inaccuracy in our results, which means this is only approximate. The distance is only approximately 5.18 units. But if you got a result that was close to 5.18 and you took a workflow that was similar to the workflow I've used to solve this question, then you did get the correct answer. So if you did get the correct answer, congratulations. This was one of the most challenging questions I've set probably in this entire series. It wasn't hard in as much as we were just following some theories that we've seen in this video and the previous video, but it's just a lot of numerical calculation when you're working it out by hand. There's a lot of room to make small numerical mistakes, and obviously a mistake early on is going to flow through your result and give you an incorrect result. in the end. So to recap everything we've seen in this video, we saw how we could use the vector representation of a line to find the perpendicular distance. Here we go. To find the perpendicular distance of a point from that line. So by representing the line with a vector equation, we were able to find the perpendicular distance. And we did that by representing everything we know about the equation and about the problem using vectors. And then we applied what we knew about that problem in terms of vector theory. And what we knew is that the length of v would give us that perpendicular distance. We knew that we could define a point Q as a point on our line using our vector equation. We knew we could find v in terms of Q and R, which meant if we could find the point Q, we could find v, and that would give us the perpendicular distance. We also knew that v is perpendicular to D, and that was the most key element, if you will. That's the most essential element to this theory. The fact that they're perpendicular, that means the dot product's equal to 0. That gave us some reference point, if you will. It gave us some equation that is equal to a known value. And from that known value, we were then able to rearrange that equation, solve that equation for the parameter value TQ, which that parameter value gives us Q. And once we have Q, of course, we were able to find V. And once we have V, we're able to find the length of V. So this was the final video on this DVD that covers vectors. So I really hope that this video has helped to illustrate the sheer power that vectors give us, especially when we're working in computer graphics and programming. Now, as I mentioned in the introduction of this DVD, I personally believe that vectors are one of the most, if not the most, important areas of mathematics that relate to computer graphics. And so I really hope that you've seen during this DVD that that is the case. Everything we've seen is showing us things that are very powerful that when we apply them to solve problems in computer graphics. And it's actually just the tip of the iceberg in terms of vector mathematics. We've only covered the fundamentals of vectors as far as I'm concerned in this DVD, but that means we have explored the core concepts, the core theories and operations that relate to vectors in 3D Cartesian space. And these concepts and theories are going to be invaluable to you, not only for solving problems, but also if you decide to study vector mathematics to a further level on your own. Because you're going to find that everything we've covered in this DVD, all of the theories, all of the proofs, all of the operations, everything, they're used as building blocks for the more advanced concepts. So all of the more advanced concepts are going to assume knowledge of everything we've covered in this DVD. So the fact that you've got this as a foundation is going to be invaluable to you, both in able to apply it to solve problems, which of course that's invaluable in itself, but also if you want to study this further, this knowledge is going to be invaluable for that. So I really do hope you've enjoyed from and benefited from the various topics that we've covered on this DVD. And if you have any questions or feedback, any feedback at all, or perhaps you're working on your own mathematical problems and need some assistance, then do be sure to head over to the forums on 3dbuzz.com, where you're going to find a community of knowledgeable and helpful members who are always happy to assist you. So thanks again for watching. I really do hope you've enjoyed this DVD, and I wish you the best of luck solving problems with mathematics in the future. Thanks, guys.